Hi, I'm Bill Peebles, and in this video I'll talk about our new paper, GAN Supervised Dense Visual Alignment. This is work with Junhyun Zhu, Richard Zhang, Antonio Taraba, Alyosha Efros, and Eli Sheckman. In this paper we tackle the joint alignment problem. Here are a bunch of photos from the Ellison Katz dataset. We propose a method that can jointly align entire datasets of complex images just like this. To get a better sense of why this is useful, let's focus on only a few images from Ellison Katz and the dataset average image. Here we show our learned transformations of these few images that bring them into joint alignment. Through the average aligned image, we can find accurate dense correspondences between all of the images. And our algorithm does this without relying on any correspondence supervision whatsoever, and despite being trained exclusively on GAN data. It generalizes automatically to real data at test time. As we'll show later on, our algorithm works surprisingly well when applied per frame to video and can be used to power a variety of mixed and augmented reality applications. Our method takes inspiration from the classic congealing work from Eric Learned Miller. Congealing showed that you can learn per image affine transformations to bring a dataset into joint alignment in an unsupervised fashion. However, it only worked on simple datasets with limited appearance variation, like binarized MNIST images. In this work, we introduced congealing. Rather than learn per image affine warps, we train a spatial transformer network that predicts highly expressive transformations of images, and it works for extremely diverse Ellison-level datasets. Of course, the million-dollar question here is, how can we actually train this spatial transformer network? The main issue is we need some source of supervision to train the spatial transformer, and it's not clear what that should be. Now, if we happen to have paired data like this, where all of the images in the right column are rendered in the same pose, but share the style of the corresponding input, training the spatial transformer network would be a breeze with a reconstruction loss. But how can we actually build such a paired data set? The key insight of our paper is we're going to use a GAN to do it. So the input images are drawn from a GAN pre-trained on the unaligned input distribution, and the corresponding target images are generated by interpolating a portion of the latent code that controls pose towards a learned vector C. Because we use the same latent code C to generate all of the target images, you can see that all of the cats in the right column are indeed rendered in the same pose. Now, this isn't a great pose. The cats look a little funky, but gradient descent will help us take care of that issue. So with this dataset, the spatial transformer will process each image, make a prediction, and we'll compare that via perceptual loss to the target image. Critically, now we can minimize this loss with respect to both the spatial transformers parameters, but also that latency which is controlling object pose. And now we've learned a much nicer template. The spatial transformer is successfully aligning fake images and automatically generalizes to align real images too. All right, now let's get back to results on real images. Here are some successful results on Ellison bicycles. Our method can handle bikes with heavy appearance variations and even out-of-plane rotation of the wheels and frame. On cub, congealing works well for birds with different morphologies and orientations. Our average congealed image is a template which can propagate anything to images of the same class. For example, by dragging a Batman mask onto our average congealed cat, a user can effortlessly propagate their edit to a massive number of images. Or a user can put a soldier onto a bird template. Or you can add saddles to horses. Or you can add unicorn horns with one of our other learned horse templates. A surprising result of congealing is that our spatial transformer empirically works well when applied per frame to videos without leveraging any temporal information whatsoever. This can be used to do single object dense tracking to power various mixed reality applications like object filters. Here are results on many videos. Note that in all cases, we always propagate annotations from our average congealed image. By annotating that single image once, users can propagate their edits to as many videos as they like without any additional annotations required. Let's look at some baselines. Congealing tends to outperform methods that rely on supervised training with pairs of real images like cost aggregation transformers, and surprisingly can even outperform RAP, which has a tendency to suffer from severe accumulating errors over time. In terms of limitations, congealing relies on being able to align an input image to the template. So if any important aspects of that template are not visible in the image, it'll tend to produce a failure result. Thanks for watching, and you can find our pre-trained models and code on GitHub.